Swayam Prabha. Digital India. Educated India.
So let's do a transfer characteristics of the amplifier. Okay. So in this particular case, let me draw the amplifier first. Again, minus plus. And in this particular case, let's just say this is your Vn and this is your Vp. Okay. And this is V out. Okay. So I'm applying some common mode signal and some differential signal. So how would we describe that when it comes to using actual voltage sources? Okay, so follow my train of thought. So let's say I would like to apply a differential signal of let's say VID. Let's say I would like to apply differential signal of VID to this amplifier. Then what we can do is, hey, that's pretty easy. I can just draw a voltage source that looks like this, okay, and that would be my VID. Okay, so we know the difference between Vp minus Vn is VID. So, however, we don't know what actual voltage Vp is or Vn is, or like what is it reference to? So we only know difference between Vp and Vn. So then what we do is, let me redraw the circuit to make a point. So I can also do something like this. So this would be minus again and plus again. So then I'm going to break that voltage source in two pieces first. Okay. And then I'm going to say, hey, let me just make this VID by 2. This is also VID by 2. So same thing, right? You can say apply plus minus plus minus. So I just broke that voltage source in two pieces with VID by 2, and this center point is my common mode potential for the amplifier. So here I can put in something called, let's call it VICM plus minus. Now let's figure out using KVL what's the potential at Vn and what's the potential at Vp. So Vn will be equal to VICM minus VID by 2, and Vp will be equal to VICM plus VID divided by 2. Alright, so this is the way we define the input voltages to the amplifier, and then you will have a V out that will be again, you have a VDD in this case. I'm just giving an example, and let's call this ground or 0 volts, and we apply VDD, and then we can say that the V out is going to be between ground and VDD. Alright, so if we plot these characteristics, how is it going to look like? Okay, so let's first plot the characteristics of the amplifier, and we know that the amplifier has a very large gain AV. Okay, let's do a simple plot first. So where I'm just plotting VID, okay, and this is my V output first. So what would be the output voltage lie between? The output voltage will lie between VDD and ground. Ground here we are saying that's equal to 0 volts. Okay, so I'm going to, for the sake of discussion, I'm going to call this as 0, and this will be my VDD. Okay, so if I apply VID, then we can call this center point, which is VDD divided by 2, as our analog ground. Okay, around which the output can be. Okay, so in this particular case, we can say that if the VID goes up, then this is what the characteristics will look like. Something like this. Okay, so if VID goes positive, then the output of the amplifier will go positive, and then because the gain is large, as soon as VID goes beyond few millivolts, the amplifier output will clip to VDD. Okay, and the slope of this line is the gain of the amplifier, AV. And as I said again, this AV, we would like it to be very large. It could be 1,000, 10,000, 1 million, something like that. Okay, so the higher the gain, more ideal the op amp will look like. All right. So once you understand this, we can also, for sake of illustration, I would like to plot this transfer characteristics as a function of what do we see at Vp and Vn, because in this particular case I'm plotting with respect to VID, and so it's also important to understand how the transfer characteristics look like when we just plot Vp and Vn also. Okay, so in that case, let's draw it here differently. I'll use a different color. All right, so this is going to be I'm going to plot Vp, which is equal to VICM plus VID divided by 2. Okay, and this is our output, V out, and output also will have some common mode voltage, which is what we are calling analog ground. In this particular case, if our VDD is right here, then we are saying that at output I have VDD divided by 2. That's where my output is. Okay, so I want you to think about it for a second, and then tell me how the transfer characteristics will look like if VICM is over here, let's say. Okay, so I'll give you 10 seconds or so and plot the characteristics. And note, I'm showing Vp over here. Okay, so Vp is given by VICM plus VID by 2. So hopefully you were able to figure out how the transfer characteristics is going to look like. So what we are going to do is we are just going to draw some few things here as a reference for you, so that okay, now when Vp goes positive, okay, we expect the amplifier to amplify the voltage quickly. Anytime Vp goes positive, so we expect if Vp goes positive compared to VICM, then we expect the amplifier to show a characteristic something like this. Something like this. Okay, and even though it doesn't look like a straight line, it should pretty much look like a straight line like this over here. Okay, all right. So let's discuss a role of the VICM. And what does VICM do in this particular case? Okay, so as I said earlier, we would like to have zero common mode gain, which means that if VICM changes, we don't want output to get affected. Okay, so that's the key point I'm trying to make here. So let's say we used a different value of VICM volts. Let's say we changed the VICM from, in this particular case, let's say it was VDD by 2, and now we moved it to maybe 3 VDD by 4, something like that. So now this particular voltage will be somewhere over here. Then can you stretch your imagination and draw the characteristics of this amplifier? What would you see? So I will just quickly draw it for you. What you would expect to see then is something that will look like this, something like this, and this is your new VICM. So this would be 3 VDD divided by 4, and what you would see is as the Vp goes around that voltage, you will see the op amp respond, and the output is still VDD by 2, because that's where the output is referenced. Okay, and in case we choose different VICM value over here, so which would be let's say VDD divided by 4, then also you would see transfer characteristics that would look something like this. Okay, let me redo that. Something like this. So for some of you it might be a little bit confusing in the beginning, but what I'm trying to explain to you is we are plotting voltage at Vp, which is VICM plus VID by 2. Now, when you do that, as the Vp, when VICM is fixed, that means the VID is the one that is changing. Okay, and what finally matters is the differential voltage between the two terminals, and what we are desiring is this particular characteristics, which is VID, and then this is your V out, and we desire this particular type of characteristics, and something like this, and this characteristic should be independent of VICM. That's what the op-amp does. And this VICM is the one that I explained to you a while ago. That's like a common mode signal, which is there on both sides when you're doing this ECG example. Okay, and what we are trying to identify is not the common mode signal, but is the difference between the two. So, for example, to give you a little bit visual imagination of how this signal is going to look like, is let's say we have this is our 50 hertz, something like this. So this is on Vp and this is on Vn, and riding on top of this would be your signal that we desire. So then that signal would be something like this here, something like this here, let's say, and then would be something like this here, something like this here. Again, I'm exaggerating substantially, and then on this side it will be on the opposite side, something like this. Okay, so as you can see, the common mode, the green part is same to Vp and Vn. However, the red part, which is what we are most interested in, is going in the opposite direction on Vp and Vn, and that's the signal we are trying to amplify. So when we feed this into our op-amp based circuit differential amplifier, then what we desire at the output would be something like this. So which would I'm just going to draw the something like this, right? So you will see something that will go like this, something like this. And we amplified the weak differential signal. However, we did not respond to any one of these the green common mode signal. Okay, so that's in a nutshell how I can explain to you the common mode signal versus differential signal. Okay. Now let's get into a little more details about how do we use this amplifier. Okay, so different circuits that we're going to attempt to do with the amplifier. So the first one is let's take the simplest example. So here is a triangle which is representing the amplifier plus and minus, right? So if we connect this and this is reference to ground here, and if I connect the negative terminal to ground, again here whenever I show these ground signals, they are all analog ground related signal. Okay, because they are some voltage which are between 0 and VDD, the supply voltage of the amplifier, and this is implicit assumptions going forward throughout the course. So you should never confuse this with like a absolute 0 of the amplifier. Okay, so this is a analog ground, and now I'm applying a positive signal here, which is, let's say, Vp. What do we expect at the output? So whenever what we would expect is when Vp is equal to 0, just like Vn, okay, we would expect 0. Okay, and this is our Vp and this is our V out. And then if the Vp goes up compared to Vn, then we would expect things to go positive, right? So this is what we expect. Pretty straightforward. Something that looks like this. And this slope of this curve would be your AV. All right. Similarly, we can do a flip case where we would apply a, let's say, let's use a different color, and I would apply a, I would change the input structure here. So here in this case, I'm going to apply analog ground to Vp, and then I'm going to apply a plus minus input source here, Vn. Okay. Then what do I expect? Then what we would see is something that would look like this, right? Something that would look like this. So this would be for the Vn case. So the red would be Vn case. So whenever Vn is negative compared to Vp, then output will go high. And when Vn becomes positive compared to Vp, then the output will go low. Okay. So this is kind of important to understand. So whenever you apply input to the non-inverting terminal or positive terminal, then the output output of the amplifier should go positive when you apply relatively positive input to the non-inverting terminal as compared to the inverting terminal. So this is pretty straightforward, and you should just kind of one thing that I would like you to do as students is I'm doing all these things in the classroom, and you're probably watching the lecture, but I would strongly recommend all of you to have a notebook and draw all these pictures, because circuit design is visual. You draw, and then once you draw the schematics, then it will really sink in. If you just look, at that time it will appear like you are getting everything, but unless you draw it without looking, the ideas will not sink in. So it's really important to draw the pictures, and you will see why I'm saying that, because of the next particular example I'm going to show you. Okay, so let's take our amplifier, right? What is the equation of the amplifier that we would like to use? So equation of the amplifier is V out equal to AV, which is large gain, times Vp minus Vn. Okay, so now I'm going to give you a schematic, very simple schematic I would like you to draw on a piece of paper, and then can you solve the what would be the output? Okay, so what I'm going to do is I'm going to apply a voltage V in over here, V in, and then I'm going to connect it in something like a unity gain feedback type of network that you may have seen, and then I'm going to ask you to write an expression for V out. Okay, I'll give you 10 seconds to write, and then I will start writing the question, writing the answer. Okay, so as I said again, we will start from this expression, and then I will just substitute the terms for these two terminals, and then what we would get is V out is equal to AV times, what is V? Positive voltage is also V out, minus Vn. What is Vn? Vn is V input. Okay, and then we can let's see, we can say AV times V in is equal to AV minus 1 times V out. So then we can say that V out divided by V in is equal to, what is that equal to? That is going to be equal to AV divided by AV minus 1. So this, since AV is really large number, you can say that, hey, that's pretty close to 1, right? So if I apply input voltage, I should see an output voltage equal to the input voltage. So if you have gotten the same answer as I have shown, then I'm going to tell you that it's actually a trick question. It's a trick interview question. In reality, the circuit really doesn't behave this way. So I'm intentionally misleading you on this path to see, how you can you can fool yourself, okay, for that matter. So let's see what is really going on. Let's think about this for a minute. Okay, let's say that the gain AV is 1 million. Okay, 100 $1 million, which means there are 6 zeros, right? 1 million. AV is equal to 1 million. Okay, all right. Now, let's say in this particular case, the supply voltage is 5 volts and 0 volts. And as I said, we will apply input voltage, which is equal to 2.5 volts for a minute. All right. So since AV is very large, that means somehow we are able to get output equal to 2.5 volts approximately. All right. So if output is 2.5 volts, then the difference between the two sides is going to be very small, right? I mean, 0. So as a result of which this one looks fine. However, what I would like you to think about is, let's say this 2.5 volts input voltage, we just take it slightly higher. Let's say we take it higher by 1 millivolt for that matter. Okay, so if I take it up by 1 millivolt, then this input voltage will be 2.501 volts. All right, I'm just lifting it up by 1 millivolt. Now what will happen? Think about it. I am taking a negative terminal of the operational amplifier and I'm taking it positive compared to a non-inverting terminal. So suddenly my difference between the two is only 1 millivolt. And it's going to get amplified by the gain of the amplifier. And what do we see at the output? Which way will the output voltage go? Now that's something that I would like you to think about. So would the output voltage go high or low? If you have answered low, then that's not correct, because we are taking negative input and we are raising it positive compared to the other input. So what we expect, whenever we touch the negative input and take it higher compared to positive input, the output is supposed to go low. So since the gain is so high, what will happen is this 2.5 volts will suddenly go to 0 volts, okay, because the gain is so high. Now, so the key point I'm trying to tell you is, the amplifier is not really behaving like this equation that we have brought out, because in this particular equation we just proved ourselves that amplifier is actually unity gain amplifier. Basically V out is equal to Vn, but that's not what is going on. And the reason for that is something called feedback. This feedback part we are going to discuss at length in future lectures, but there are two types of feedbacks. Okay, there is a positive feedback and a negative feedback, and negative feedback is something I'm sure you have experienced it all the time. How you do in the exam, and your parents will give you some feedback, right? And generally it's a hopefully feedback which will improve the situation, right? So in this particular case, if you look, the feedback is actually positive. What that means is, if for some reason the input is going up, then the feedback will make the situation even worse. Okay, so it will amplify and make the difference between positive and negative terminal go in the same direction. So another example of a positive feedback that you can imagine is many times you go for a concert or some kind of program, and then the person who has a microphone goes very close to the speakers. So in that case, what's going on is, whatever you speak inside the microphone is going through the microphone, is getting amplified, coming out of speakers, and from speakers again it's going back into the microphone. And when something like this happens and the two signals are going together, then we will get something called positive feedback. And the positive feedback generally in the amplification type of situation is not a good thing, because it would latch up the system one way or the other. And in the amplifier case, you will hear the speaker microphone case example that I gave you. It will latch up. It won't latch up. You will just hear a really loud tone, which is kind of the other mode of operation of the amplifier, which is like an oscillator. Okay, we are going to touch up on that later on. Now, coming back to this particular example, this is an example of a positive feedback. Okay, so watch out for feedback before you start analyzing the circuits, because you may fool yourself. You may assume that the circuit will behave in certain way, only to find out that the positive feedback will spoil the party. Okay, so to have a negative feedback, you would draw the circuit in this fashion. So the classic example would be something like this. So you have positive input, negative input, and this is again V out, which we call it positive output. So this, we need it to go over here. So we can see now we have a negative feedback in this particular loop. In the earlier case, we had if you look at this particular loop, feedback loop, it's positive feedback. There is a positive sign. So here, if you look at this particular loop, there is a negative feedback. So in this particular case, what will happen? Let's take an example, right? Let's say same example, this is 2.5 volts and output is also 2.5 volts, so that there is no difference between the two terminals. And now if V out goes positive, okay, let's say this goes up by 1 millivolt. So this becomes 2.501 volt. Okay, so here in this case, the positive input is going positive, which means the output will also follow, and here this will also become 2.501 millivolts approximately. Okay, so you can see now, since this went up along with it, the difference between the two terminals VP and VN still stayed 0 or close to 0, and as a result of which this circuit is in a stable operating point. Okay, so let's solve the equation for this one. I'll give you another minute, not a minute, 10 seconds to solve. It should be pretty straightforward. So V out is equal to AV times VP minus VN, and in this case we can substitute VP, which is, what is VP, is V in, and Vn is equal to V out. Okay, and you can quickly prove it to yourself that V out over V in is going to be equal to AV divided by 1 plus AV. And that's, if AV is large, and that's the reason we say all the time that voltage gain of the amplifier has to be, operational amplifier has to be large, so that this number comes out to be almost equal to 1, okay, when AV is large. Great. Okay, so in the next part of the lecture, we are going to go through a few more examples of circuits with operational amplifier.